So what I want to do in this session is go through some more examples of this spectral classification. How do we identify the spectral class of stars? If you haven't watched the video and gone through the notes on spectral classification yet, you should do that, because that's the video where we talk about why different spectral features show up at different temperatures. We did a few first examples of going through this kind of a graph and saying, well, for what spectral classes are different spectral lines more or less prominent, and how to identify those. So if you haven't gone through that material yet, make sure you do that before this, because then things will make a lot more sense. And again, we're going to be using this Sloan Digital Sky Survey. Again, this is a open source access. This program is constantly measuring the properties of stars across the night sky. And there are hundreds of terabytes of data that you can access here. This is the same kind of data that researchers use to study astronomy. So this is not, this is the full detailed stuff. So in order to access some of the spectra, there's a whole bunch of different ways that you can use this and access spectra. That you can basically get a picture of the sky and look around to different parts and find objects and see if they have spectras available. You can do different kinds of intense searches for stars with specific properties. This is more for research purposes. I think one of the easier ways to get this is to go to More Tools and Get Plates. Now, I'm hoping this runs. Okay, this was running a little slow for me earlier, so I'm glad this is working. And there are a whole bunch of different surveys where you can get a ridiculous number of spectras of objects. So you can pick a survey and identify what plate, basically what particular image of the sky you want to analyze. And there are thousands of options to choose from here. And for each of these options, if you click on one, so I'm just going to click on one at entirely random, let's do that, and get a plate. Each one of those plates for this particular survey will be able to track up to 640 individual objects and get their spectras. So we've got thousands of plates, each one with hundreds of objects on them. And this is only one of the surveys. This isn't even the full data set. So again, there is a ridiculous amount of information. So let's just pick some stars entirely at random. Sometimes you'll get stars that look like this, where this axis is not large enough to really identify many of the features. When you're looking for stars, you want them to be brighter. And this is something I should have mentioned earlier. This vertical scale is basically the intensity of light. So the larger this scale is, the brighter the star is in this particular part of the spectrum. So this one is not bright enough. I think I want to get a different one. Let's try another random star. Okay, let's do this one. So notice that the brightness is fair bit higher, even though it's not really at lower temperatures. So let's take this star and start to graph some of its properties. Okay. So what do we have? For Wien's law temperature, well, actually, you know what? Try this one yourself. Try to identify the temperature from just the shape of the graph, kind of an approximation overall. Identify if there's hydrogen features, ionized metals, neutral metals, and molecular bands. So pause the video and try to analyze this particular star on your own first. Okay, so hopefully you actually are pausing it and giving this a try. If we look at the overall shape, it's pretty low until we get over here, and it's going to peak far to the right. So this temperature, very low temp. Let's look at some of the features. So the hydrogen lines, you've got hydrogen alpha, hydrogen beta, hydrogen gamma, and hydrogen delta. I pretty much don't see anything there. So this is a none. Now, why did that change to that? So that's none. Ionized metals, you can't really see it. These are computer generated, so it doesn't always display the data perfectly well. This would be where the H and K lines are. Nothing. So that's none. Where is sodium and magnesium? I think those are off the graph too. I think this one would be sodium. This one would be magnesium. Again, I really don't see anything there other than noise. But what I do see are these wide molecular absorption bands. All those things. I would say that's strong. So if we have strong molecules and pretty much nothing of anything else, this would be a low temperature M star. So this would be a very low temperature M star. Notice that it does actually say what classification type the star is. This will not be included generally on the spectra that I give you. I will remove that from there, but again, it's a way to kind of double check some of these. So that one, really low temperature star. Only features we see are those molecular bands. So this one is clearly going to be an M star. Okay, let's try another one. So again, I'm just going to pick a star at random. All right, let's try this one. Here we go. Okay. So for this one, again, pause the video and have a go at this yourself, and then we'll kind of talk about that one together. Again, identify those features and see if you can identify what spectral class it is. And let's pretend that we can't actually see what that spectral class is to begin with. Okay, so if we look at the overall shape, that peak of the graph still pretty low temperature. So temperature is still low. But let's look at some of these other features. Hydrogen series, hydrogen alpha, beta, gamma, and delta. Not much. Again, it's hard to tell what's noise and what might be a nearby spectral feature, so pretty much none here. The H and K lines, again, that's kind of off the graph here, but that's where they would be. Not seeing much. For the neutral metals, well, that's our sodium line and that's our magnesium line. Notice we've got these deep kind of cuts into the graph, so I'd put those as pretty strong. And for those bites out of the graph, I'd say, well, that's a kind of smaller bite. Okay, there's a couple of those, not nearly as dramatic as some of the ones that we were looking at earlier, so I'd put that at maybe medium. So we've got strong neutral metals. We've got not really any hydrogen, not really any ionized metals, little bit of molecules. So I'd probably put this at a cool K or a hot M. And if we look at what this one actually is, K7, remember the numbers, as you go up in numbers, that's a lower and lower temperature. So K7, 8, and 9, those would be the lower temperature K stars. Again, I would not expect, if I was giving these sort of things as a question on what spectral class is it, I would give you a spectrum and say, is this most likely an O, an A, a J, or an M? Sorry, a G or an M. I'm not going to be hyper precise because we literally don't have the tools to be super precise about this, but we can get the general idea for these. Let's see if we can find another one. So I'm going to actually try to get another one and erase the label on it. So I'm going to pause this and come up with a new one so we don't kind of spoil what it actually is. Okay, so I picked another one and I've blocked out what the special class is for this one. So pause the video again, take a look at this one and see if you can identify what kind of a star this one is. So pause the video and have a go for this one. Okay, well, let's go through this. If we look at the shape of the spectrum, notice that this one, the peak is pretty far to the side. So I'd put this on the hotter scale. Not ridiculously hot, but, you know, hotter than definitely the last two that we were going through. And let's look for some of the other features. So the hydrogen features, hydrogen alpha, beta, gamma, and delta. So there, and there. Yeah, I'd say those are pretty strong. For the ionized metals, we can finally see this on the graph, the H and K lines right there. Those ones, yeah, very strong. What about our sodium and magnesium lines? Well, I can see a little bit of a dip down for both the sodium and magnesium, so maybe I'd call that weak. And I don't really see any of those wider bands cut out of it. Like if it's part of a spectral line, this kind of part right here where it kind of makes a bit of a cutout, that I would just say is part of the spectral line itself. That's not a separate molecular band. So I would say none for this one. So if we look at this, we know it's going to be in the hotter, one of the hotter spectral classes. Hydrogen features are pretty strong, so maybe somewhere in here. Ionized metals are also very strong, so somewhere in there as well. So it looks like this sort of bracket we're looking at. Also a little bit of neutral metals. So yeah, I'd probably put this somewhere around F class, maybe a cooler F class if it's got a little bit stronger. Maybe if it's a little bit stronger ionized metals, I might put that at a cooler F class. And if we look at this one, yep, that one is an F5 for this particular class of star. And again, for these questions, I'm not going to ask for a hyper accurate measurements, just kind of approximately how do these stars compare with each other. Another thing about this one is notice that this would be a very, very bright star. Because if we look at this scale of how bright the object is on the sky, that goes up to 200. So that would be a lot brighter than some of the other stars that we're looking at. This is also being looked at with a telescope. So I'm guessing that this still wouldn't be able to be visible with your own eye, but it's brighter than some of the other stars that we were looking at. I'm going to pick one more, and I'll do the same thing for pausing that and getting a new star here. Okay, here's another one. Again, pause the video, have a look at this one, and see what you can identify for what this spectral class might be. So take a minute to do that. Okay, so let's talk about this one. Again, this one is peaking very high on the shorter wavelength part of the spectrum. So this is that shorter wavelength. So this is a high temp. In terms of the hydrogen features, hydrogen alpha, beta, gamma, and delta, these are all pointing down pretty strongly. They've got a little bit of width to those spectrums as well. So I put this as strong. In fact, this one actually looks kind of similar to the last one. These H and K lines, well, the H line is a little bit weaker. The K line is a little bit stronger. So I'm going to call this one medium. Again, for the purposes of our analyses, all of these features together, we're just going to kind of average their strength. One is a little bit, for this K and H line, the K is a little bit smaller. The H is a little bit larger. Call it a medium. Neutral metals, well, that's here, and I can't really tell what's noise and what is a spectral feature. So I'm going to basically just say none for that. So that would be weak to none. And again, not seeing any molecular bands. So in this case, well, we've got the really strong hydrogen features. The ionized metals are kind of more at a medium level. Neutral metals are gone. We don't see that at all. So it's got to be, somewhere to this side. So I'd probably put that at an A for this one. Those strong hydrogen lines, are really indicative of we have a type A star. And when we check the type of it, okay, that would be an A0 star. Again, that one was kind of similar to the last one. The difference between the last one was the last one, it had stronger, a little bit stronger sodium and magnesium lines, and a little bit stronger H and K lines, which is why for the previous example, we said maybe it's a little bit more over here, more ionized metals, a little bit of neutral metals, maybe a touch less hydrogen. But again, that's how we can kind of compare and contrast some of these. Notice in this case also, the last star was much brighter than this one, because if we look at these values for the brightness, that scale is very different. So if the question is asking you about the brightness of an object, check out that scale to see, you know, is it in the tens or is it in the hundreds for how bright these stars are? Let's actually do one more. I know I said I was going to do just the one, but let's do one more after that. Okay, so this is the last one that we'll try. Again, try pausing the video and identifying what the spectral class of this star is. So take a minute to do that. Okay, let's talk about this one. So let's look at some of these features. So overall, the temperature of the object. Well, some of the last ones were way over here. So I'd probably put this at like a medium temperature. In terms of the hydrogen features, we've got alpha, hydrogen beta, hydrogen delta. I think hydrogen gamma is somewhere around here. That's probably medium. That's maybe a little bit, or sorry, that's probably medium. That one's a little bit weaker. I'd probably put this at, you know, medium to weak. So let's do weak to medium. H and K lines for ionized calcium. Well, those are pretty strong. So these are strong. What about our sodium and magnesium lines? So here and here, I'd probably put those at probably, again, like weak to medium. So weak to medium. And notice there are a couple of parts where it looks like we might just be getting the very starts of some of these molecular bands. So I'd say maybe for the molecular bands, very weak. Again, what you call very weak, if I call it weak, or again, those sorts of discrepancies, I'm not worried about that high level of accuracy. But again, we should be able to kind of generally find out what kind of spectral class this is. So for this one, well, let's kind of go through this one. The strongest features are the ionized metals, so probably somewhere in this strong ionized metals. We've got weak to medium for both hydrogen. So hydrogen is the weak to medium, that's that line that lines up. And the neutral metals are also kind of weak to medium. And the molecules very weak, so I might put it kind of over here, probably a type G, something like that. And if we take this one, that's a G2. So again, that would be on the hotter scale of a G. G0 would be the hottest, G1, G2. Actually, our own sun is a G2 star. So this one is very much like our own sun. And just to kind of finish this up, let's actually check this against Wien's law. So if we wanted to try Wien's law, we'd say, well, the peak of this graph, that seems to be showing up around 5,000 angstroms. So lambda max, if it's 5,000 angstroms, you divide by 10 to get the wavelength in nanometers. So that would be around 500 nanometers. Again, I probably didn't draw this exactly right, but within a error range. So that's around 500 meters. And then suppose we wanted to use Wien's law. I'm going to do this over here, where lambda max times T is, I'm going to have to erase some of those notes. Let's clear that. Lambda max times T is 2.9 times 10 to the 6. Well, pause it, take a minute and see if that lambda max, if this was 500 nanometers, what would we get for the temperature? So pause that and give it a try. Well, basically you take that equation and divide both sides by the 500 nanometers. In this case, it's exactly the same as we had for the sun. The approximate temperature is 5,800 Kelvin, which again is in that range for what we were talking about for a spectral class G. It's on the higher temperature part of that range for a type G star. So again, for these kinds of spectral classifications, the composition of these stars are all pretty much the same. So even though this one has some, moderate, weak to moderate sodium and magnesium lines, it does not mean that this star is mainly made out of sodium. It does not mean that most of the star is made out of ionized calcium. We're just saying it's at the right temperature for those spectral features to become very prominent. So if we see those prominent features, we can identify the temperature.